In this video, we're going to look at how to compute volumes of solids of revolution using the washer method. Sometimes when we form a solid of revolution by rotating a region in the plane about a line, we obtain a solid that has a hole. Consider the region sketched here between the blue and the red curve, and let's suppose we wanted to rotate this region about the x-axis. First, note that this region does not border the axis of rotation, which is the x-axis in this case. We've seen that if the region bordered the axis of rotation, our cross-sections will end up being disks, and since the region does not border the axis here, we're going to get something different for our cross-sections. So here is a sketch of the solid that we obtain by rotating this region around the x-axis. If we look at this region from the outside, the solid will look like the solid shaded in blue here, sort of a bowl sitting on its side. And if we look at it from the inside, we have the sort of red solid in the middle that's missing. So we have a cylindrical-like hole through the middle of this solid that is missing. If we take an arbitrary cross-section, such as the one shown in green here, and we pull out that cross-section, then what we're going to see is that we have a disk on the outside, but another disk in the middle that's removed. And so this cross-section will look something like this. And this, based on its shape, is often referred to as a washer. And so when we have a solid of revolution like this, by rotating a region that is not bordering the axis of rotation, we're going to form cross-sections which are washers and use the area of our washer to find the volume. The first thing that we need to do is to determine the area of our washer. Each washer is going to have two different radii, an outer radius, which we'll call capital R of X, and this will be the radius from the center of the washer out to the outer edge of the washer. And we'll also have an inner radius, which we can call lowercase r of X, and that will be the distance from the center of the washer to the inner rim, or the inner circle of our washer. To find the area of our washer, our cross-sectional area A of X, we're going to first find the area of the entire washer, including the missing circle, and that is just pi times the outer radius squared. So this will be the area of the washer plus the area of the missing circle in the middle. And we can adjust by subtracting the area of the missing circle to get the area of just the washer. And so we could subtract pi times the inner radius squared from pi times the outer radius squared. And we can simplify this a little bit just by factoring out a pi. And so the area of our washer is simply going to be pi times the quantity outer radius squared minus inner radius squared. Well, once we have this, then we know our volume of our solid, where we have washer cross-sections, such as this, will be given by the definite integral from a to b of this function, pi times the outer radius squared minus the inner radius squared, dx. And of course, this could be converted to an integral in terms of y as well, by just simply rewriting the radii in terms of the variable y. In this example, we want to find the volume of the solid that we obtain by rotating the region bounded by the curves y equal x, y equal 1 over x equal 1, and x equal 4 around the x-axis. Our first step will be to sketch the region and the solid that we're going to be considering here. And so we want to sketch the line y equal x, which we know is the line through the origin with slope 1. So I'll sketch that here in blue. We also want y equal 1 over x, which is a hyperbola. And we know it's going to look something like this. And that is sketched in red. And then we want to look at this region from x equal 1 to x equal 4. Well, x equal 1 we actually know is the point where these two curves will intersect, and x equals 4 will be over here somewhere. And so now that we have sort of this region all sketched out, we can actually erase everything from both of these curves that lie bigger than 4 or less than 1. And so we can get rid of most of our curve here. And so our region that we're going to be considering is this region right here. This sort of triangular looking region, although it's not exactly triangular because the red curve there is curved and not straight. We are going to be rotating this around the x-axis. And so when we do that, we will get a mirror image of our region in the fourth quadrant. And so it'll look something like this. And so our entire solid here will look like various washers at different points. The outside of our washer will be given by the rotation of the blue curve, and the inside of our washer will be given by the rotation of the red curve. And so if I take out our washer here, what we need to do is determine the area by looking at the outer and inner radius. So here, our outer radius will be the distance from the x-axis out to our outer curve of our region, which is our blue curve, which is y equal to x. And so our outer radius here will be just simply x. And our inner radius will be the distance from the x-axis to our red curve. And our red curve is given by the function 1 over x. And so our inner radius here will be 1 over x. And once we have all of these values, we can see that our region here is going to live between x equal 1 and x equal 4. That is our, that's given to us as our bounds for our region. So now we have all the ingredients that we need to be able to compute the volume of our solid. So we substitute our radii and the endpoints of our solid into our integral formula and evaluate it to compute the volume. So we know our volume will be given by this definite integral from 1 to 4, since our solid lies between x equal 1 and x equal 4. Since we have washers here, we're going to have pi times the outer radius squared. Our outer radius was seen to be x, and so we square that to get x squared. And we're going to subtract from that the inner radius squared, which is 1 over x, quantity squared, which will just be 1 over x squared. And so this will be the integral that we need to compute that will give us the volume of our solid. So to evaluate this integral, we can rewrite 1 over x squared as x to the negative second power in order to use the power rule more easily. And so we're going to obtain an antiderivative of pi times the quantity x cubed over 3 plus x to the negative 1. And that'll be evaluated from 1 to 4. And here it does become a positive because we're going to be dividing x to the negative 1 by negative 1. And so we subtract the negative to make a positive. And so that is, in fact, a positive there. And so when we substitute in 4 to this expression, we're going to get 4 cubed over 3, which is 64 thirds, plus 4 to the negative 1, which is 1/4. And then we subtract from this the expression with 1 substituted in, which will be 1/3 plus 1. And when we do all the arithmetic here, we end up with a final value of 81 pi over 4. And so our volume will be 81 pi over 4. If you'd like to try a similar example, pause the video and find the volume of the solid obtained by rotating the region bounded by y equal the square root of x, y equal 1 over x equal 1, and x equal 3 about the x-axis. Resume the video, and the full solution will appear in a few seconds. Here we first sketch the region which is the region bounded above by y equal the square root of x, the blue curve shown here, and bounded below by the curve y equal 1 over x, which is the red curve, going from x equal 1 on the left to x equals 3 on the right. When we rotate this region around the x-axis, we obtain the solid shown here. From the outside, it looks like a blue bowl. It's kind of sitting on its side, with a hole indicated by the red solid in the middle hollowed out. When we take a cross-section, such as the green one here, we do obtain a washer, since our region does not bound the axis of rotation, which is the x-axis here. By analyzing the washer carefully, we see that our outer radius will be the distance from the x-axis up to the blue curve, which will be an outer radius of square root x, and our inner radius will be the distance from the x-axis to the inner red curve, which will be 1 over x. We're also given that our region is between x equal 1 and x equal 3, and so this is everything that we need in order to evaluate our volume integral. So our volume will be the definite integral from 1 to 3 of pi times the outer radius squared, which would be square root of x squared, minus the inner radius squared, which is 1 over x quantity squared. This simplifies to the integral from 1 to 3 of pi times x minus x to the negative second power. We can find the antiderivative of that function, which is pi times x squared over 2 plus x to the negative first. Evaluate that from 1 to 3, and we obtain a final volume of 10 pi over 3. In this example, we're asked to find the volume of the solid obtained by rotating the region bounded by y equal x and y equal x squared around y equal to 2. This example differs from previous examples in a few different ways. First, notice that we're not rotating around the x or the y axis in this example, but rather another horizontal line, y equal 2. We're also not given boundaries for x. In previous examples, we've been told that the solid would be between x equal 1 and x equal 4, for example, and so we know to use those values in our integral. And so here we're going to have to determine those values for ourselves before we're able to compute the integral. Our first step is to sketch the region that we're going to be rotating. Here that region is bounded by the line y equal x, which is shown here in blue, and the parabola y equal x squared, shown here in red. The region that are bounded between is the blue shaded sliver between these two graphs. Notice that we only drew the portion of the line and parabola that we need to enclose our region. Of course, these curves continue on both ends, but those parts of the curve will not contribute to our region in any way. Also notice that we have our axis of rotation y equal 2 labeled as a black dotted line. When we rotate our region about the line y equal to 2, we obtain a solid like shown here. The outside of our solid is given by the red curve, so it's a sort of a bowl-like shape with a parabolic side. And our inside, our hole through the region, will have a smooth linear slope formed by the blue line. When we take a cross-section of this formed at some value of x, our outside of our washer is formed by the red curve being rotated around, and the inside of our washer is formed by the blue curve. And so our washer here is this region here between the red and blue curves rotated around. Now, when we go to compute the radii here, we have to be a little bit careful because it's going to involve more than just looking at the equations for the blue and red curve separately. Suppose, for example, that we want to find the outer radius of our particular washer in green. The outer radius would be the distance from the center of our washer, which lies on the line y equal 2, and it will go down to the very bottom of our curve, which would be the point on the red curve corresponding to that value of x. Now, the distance between that corresponding point on the red curve and the x-axis is known to be x squared. We also know that the total distance from the x-axis up to y equal 2 is exactly 2 units. And so by looking at the purple segment, the red segment, and the gold segment combined, we can see that our purple segment, which is our outer radius, is going to be the whole distance from the x-axis up to our center of the washer, which is 2, reduced by the distance from the x-axis to the red curve, which is x squared. So our purple value, or the segment here, this purple segment, will have length 2 minus x squared because it's formed by taking a segment of length 2, which would go all the way down to the x-axis, and removing the little sliver here between the x-axis and the red curve, y equal x squared. We can find the inner radius using a similar approach. We want the inner radius to be the distance from the line y equal 2 down to the blue curve. Here we know that the distance from the blue curve down to the x-axis will be given by the quantity x, since that's the equation for the blue line. And so using this along with the distance from the line y equal 2 to the x-axis being 2, we see that our inner radius is going to be that distance of 2 subtracted by the value of x. So here we have the gold bar of 2, removing the dark purple bar of length x to obtain the yellow bar of length 2 minus x. And so here are the two radii for our washers in this example. We also need to know the left and right endpoints of our region. And in this case, those are probably easy enough to determine just by looking at our curves and figuring out what values we have where they intersect. However, for more complicated curves, we might need to do some algebra to figure this out. The algebra is very straightforward. We're simply going to set our two curves equal to each other. So in this case, we have x squared and x as our two curves, and so we just set x squared equal to x and solve this equation. One approach to solving this involves subtracting x from both sides, so we have x squared minus x equal to 0. We can then factor out an x from the left-hand side, and we get x times x minus 1 equal to 0. And once we have a product equaling 0, we can simply set each of our factors equal to 0, and that gives us our values of x equals 0 and x equal 1. And so these will be our endpoints for our integral that gives us our volume. So our volume will be given by that integral from 0 to 1 of pi times the outer radius squared. And as previously seen, our outer radius is 2 minus x squared. So we want to square that expression. And we want to subtract from that the inner radius squared. And the inner radius squared is 2 minus x. And so we want that to be squared as well. And so this is an integral that will give us the volume of our solid. Computing this integral is not difficult, but it is a little tedious because before we do any kind of calculus, we need to simplify the expression in brackets by squaring out each of the terms and then subtracting and simplify by combining like terms. The details are going to be left to you, but when this is done properly, the correct volume should end up being 8 pi over 15.